this thermal camera over here has a certain bandwidth that it could receive. So if I were to tune that bandwidth, and knowing that certain bandwidth would be within the physical light frequency and certain bandwidth will be outside. So if I were to slide this bar over here, you see that now we have a more distinctive contrast. So this more distinctive contrast, you would be able to see more of the features out there. Okay? So what I want to say is that just like the movie Predator, where it's able to switch its eye to receive certain frequencies. Right? So obviously all of you would have more or less about the same temperature. None of you having fever, or else I'll have like a super white color over here. So if there's a lot of various different temperatures, I could switch my eyes to receive that certain frequency bandwidth so that you will show out in that frequency band. So that's what the thermal camera is able to do. Selectively look at certain electromagnetic wave frequencies. So if your heat, right, that maybe body or maybe an object that's producing heat, there's very small level of heat, what I need to do is to tune this down to a level that I could see even the slightest temperature difference. Okay? So if something is very bright or very hot, then I'll turn it up to this stage. So now, if someone were to be seriously hot, for example, this one right here, all right? Now, if I would turn it over, look at it, and then I turn it on. So obviously, this one is very hot, hotter than your surface temperature. Now, I use a thermal camera, I'm able to spot it. That's because I'm able to selectively look at certain surface temperature so as to spot those features. So this is one good use of the thermal camera. Later on after lecture, if you're interested, you can come down, take a picture of yourself. Is able to do that? I can see it.
Selfie.
Thermal selfie. Okay, let's have a look at this now. I'm going to derive this equation over here. This equation is critical because it relates to what we were very familiar with. Remember, V is equal to IR. We drew that analogy in conduction. I is equal to V over R, where we were talking about how can we get thermal resistance for conduction and convection. In radiation, there's also this thing that's called radiation thermal resistance. So let's have a look at what are the governing equations. So I'm going to sketch out, I'm going to move to one side. This derivation is maybe about 10 lines. So I don't think you have space over here. You can write it somewhere else. That's fine. Derivation is not tested. We don't test derivation. We test application. So if I have a surface, and this surface has what we were saying just now as incident radiation, but the technical word for incident radiation is actually called irradiation. So if you were to hear irradiation, that means that's the incident radiation. Now this incident radiation could be reflected. And if it's reflected only, that means nothing is absorbed and nothing is transmitted, then you would say that this incident radiation has a ratio that's rho G. Right? If I were to look at another situation, in this situation I have this surface that has a certain surface temperature. So if this surface has a certain surface temperature, itself we know is going to radiate heat. And this radiated heat is equal to emissivity multiplied by the black body energy that's emitted. How this came about is because we had this equation before that we saw just now. Right? So it's just manipulating that, and then you get to this point. That is if there's a surface temperature. Now, if you take these two and add it together, because for any object, besides itself having a surface temperature that is able to radiate heat, it also will receive radiation from the ambient, and then out of which it will reflect some of it. So if you add these two, it will be equal to a radiative heat, or what we call the irradiation, coming in, and then you have part of it that's reflected, and by itself it has a surface temperature, so it has this emitted radiation as well. So these two together, we call it J, and J has a unit of watts per meter squared, and the term for J here is called radiosity. G over here is irradiation. So please know the names of these terminologies. If I were asked what is radiosity, please don't say it's a radio frequency. When we talk about radiation, radiosity is a combination of your reflected irradiation plus the energy that's radiated due to the surface. So J is equal to E epsilon B plus rho G. Now from Kirchhoff's law that we saw just now, some people pronounce this as double H and double F. Some people pronounce this as Kirchhoff's law, depending on the language that you speak. So Kirchhoff, Kirchhoff. So Kirchhoff's law says that if I have rho plus alpha that's equal to 1, my rho will be equal to 1 minus alpha, because there's nothing that's transmitted. So rho plus alpha, is the tau is equal to 0. So rearranging that, equal to that, and rho will be equal to 1 minus epsilon. Right? Because Kirchhoff's law says that your epsilon is equal to alpha in an enclosed area. Enclosure. So I'm going to replace this rho by 1 minus epsilon. So I'm going to get this 1 minus epsilon G. So radiative heat gained per unit surface area, hence will be equal to Q divided by A, that's your radiative heat gain divided by the unit surface area A. That one will be equal to J minus G. But you could see this written over here in your sketch, where you have Q divided by A that's equal to J minus G. That's because your G is whatever that's incident upon it. Your J is whatever that's emitting from that surface. So kind of like the resultant radiative heat will be equal to J minus G. So I'm going to substitute the following J term into it. Epsilon EB plus 1 minus epsilon G minus G. So once I have that, I could simplify it further. I could start to multiply G inside, and then plus G minus G, I will get epsilon G. Okay. So could you see it? If you were to multiply inside, there's a plus G here, and then there's a minus G there, and then you have that, I think this minus epsilon G. So I have a common factor that's epsilon, I can bring it up. So EB minus G. And what I'm going to do next is to multiply my epsilon inside. And multiply and divide by the same factor at the top and the bottom. 1 minus epsilon EB. Divide by 1 minus epsilon. Minus epsilon, 1 minus epsilon over 1 minus epsilon. So I'm not really including anything different from the previous line. But why I'm doing that is because I want to bring out a common factor. This common factor is epsilon over 1 minus epsilon. And whatever that's left in there, I'll multiply it. And I get the following term. 1 minus epsilon G. So this term over here, I wonder, could you see that it's actually equal to EB minus J, right? Where you have just now that J term is given by this expression. Okay? So you could see that J is this whole term over here. So I'm substituting it back. So now that I have that, I can re-express this whole thing in the following way. Q equal to epsilon A EB minus J divided by 1 minus epsilon. So I could bring that numerator to the bottom. That will be EB minus J divided by 1 minus epsilon divided by epsilon A. And this is what we call your surface resistance. So this surface resistance is very similar to the thermal resistance that we had seen before, but in radiation we don't call it thermal resistance. We call it surface resistance in this case for that surface. Because that surface would have a certain emissivity value that's given by epsilon. So that surface, which is a real surface, would have a certain emissivity, and we take note of that emissivity of that surface and say that it has a certain surface resistance if it wants to emit radiative heat. Okay? So that's the meaning of this surface resistance over here. And the units for surface resistance is meter to the power of minus 2. And obviously your Q would have the units that is watts. And this numerator over here would have the units that is watts per meter squared. So if I were to sketch that resistance circuit, now it's going to look like this. You have, again, your Q, that's just like current flowing through it. EB, which is your emitted energy due to the black body surface. J here is your radiosity. And your so-called thermal resistance is now called surface resistance, and is given by 1 minus epsilon divided by epsilon A. So this is your surface resistance. So that kind of like derived what we could see up here. Right? This derived this expression over here. That's how it came about. So in that denominator, that is your surface resistance. So it has the analogy just like I equal to V over R. This is what we call the potential difference, EB minus J. If you have two objects, and out of these two objects, they are radiating heat to from one object to another object. So say, for example, this A1 object is radiating heat to A2 object. So if that happens, we call that heat transfer is from Q1 to 2, Q1-2. So it means it's radiating heat from the surface 1 to the surface 2. And we know that the total energy that's leaving this object A1 that reaches object A2 is given by J1A1F12. So that F12 was our shape factor that we saw before. J here now refers to your radiosity. So the radiosity includes your radiative energy due to the surface temperature and also due to the incident radiation that's reflected out. So that's your radiosity. The object 2 would also, due to its surface temperature, able to radiate heat. Although if, let's say, A1 object, if it's at a higher temperature, then the net radiative heat is coming from A1 to A2. But A2 itself, if there is a surface temperature, is also able to radiate heat. So that radiated heat is given by J2A2F21. F21 here, this 21 refers to the heat that moves from the object 2 to 1. There's a shape factor due to 2 to 1. And we have seen before that the shape factor due from 1 to 2 is actually the same as 2 to 1. So that's why we have this reciprocity relationship that says that A1 F12 is actually equal to A2 F21. That is the reciprocal relationship. So if I want to find out what is the net heat transfer from 1 to 2, then what I need to do is to take that J1A1F12 minus J2A2F21. Later on, there will be an example to work on that. Now on this side here, we also want to talk about another very interesting thing. Just now we were saying that there is a surface resistance. But if you have two objects, besides that surface resistance over here, due to the surface, there's also the space in between, of which we call this part, I'm not going to derive that, that came about actually from here. So this is equal to J1 minus J2 divided by 1 over A1 F12. So this part over here is what we call the space resistance. So this is unlike your convection conduction that you have seen before. If I have two objects, this object is going to have the surface resistance, that object is going to have the surface resistance. The fact that these objects are placed apart from each other, in between them, there is another resistance that is called space resistance. So if heat, radiative heat, were to transfer from one side, one object to the other object, how many resistances are there? There should be 3. Space, the surface resistance, space resistance, and then surface resistance. Okay. So please remember this one. We'll solve an example so that you could see that. So for any two objects, there will be 3 resistances: your surface, space, and surface resistance. So I think that's kind of like summarized in this figure over here. So if you have this object with the radiative surface energy, that's EB1, and the other side that's EB2, how we write out that thermal circuit? This part here would be the energy that's leaving surface A1, and that relates to the emissivity, and we call this the surface resistance. And this part over here would be the energy that's leaving surface A2, and this resistance over here is also a surface resistance. And in between them, because there's a space in between them, we call this as our space resistance. Now, some textbook actually wrote space resistance using another word. Sometimes you get to see area resistance. Actually, area or shape factor resistance. Some textbooks will write in that way. But over here, we're going to call it space resistance. If you just see the other words like the area or shape factor resistance, they mean the space resistance. So you need to memorize this kind of expression for your resistance, both for your conduction, and your conduction is split up into the plate conduction, cylindrical shape conduction, your thermal resistance over there. You need to memorize your convection thermal resistance. You need to know your surface resistance for radiation and your space resistance, all these expressions. So now, if you have multiple objects, 3 objects, 1, 2, 3, you would know that the energy that's entering or leaving surface A will interact with the energy that's entering and leaving surface 2, and then so as your energy that's entering and leaving surface 3. If I were to sketch out all the thermal resistances, it's going to look like that. You have this part as a surface resistance of your object 1. This one as a surface resistance of object 2. This one as surface resistance of object 3. And in between them is in parallel circuit. Right? This is your respective space resistances. So the more objects that you have, the more complicated it is, and actually the more simultaneous equations you need to solve. Okay? Later on, we'll try to simplify this case over here. This would have a lot of simultaneous equations that we need to solve. But there's one way that we could do to simplify the case. If we consider some limiting cases, 2 limiting cases. The first limiting case, if this surface over here is perfectly insulated, and what that means is that it must re-radiate all the energy that's incident on that surface. It has nowhere else to go, right? Nowhere else to go, because it's perfectly insulated. It must re-radiate all the energy. If that's the case, then your expression over here, where you have your thermal resistance, and this one